Now, talking about this project case study for predictive maintenance using AIML. All right. Now, in this, we are going to talk about the predictive maintenance using artificial intelligence and machine learning. I'm sure you will find this very interesting. I'm sure especially people who are in IC engines and who loves this topic called turbocharger will enjoy this. Here is a realistic and detailed case study on project of predictive maintenance using AI ML in the vehicle in the context of vehicle diagnostics, particularly for commercial fleet operator. Now, case study is predictive maintenance of diesel engines in commercial truck fleet using AI ML. Now, just imagine there's a company called Fleetco Logistics Private Limited, and it is operating almost 1,000 diesel trucks across India for long haul transport. The objective of this project is to reduce unplanned vehicle breakdowns, optimize maintenance schedules, and lower service costs by implementing predictive diagnostics and engine turbocharger failure using AI ML models. The problem statement is in this company, frequent turbocharger related breakdowns are happening often in remote areas. Or remote areas means where there is no accessibility to service stations. And because of this, truck has to be towed and repaired on highways, increasing downtime and costs. All right. And reactive maintenance was proving very expensive. So instead of reactive maintenance, how can we proactively maintain? That is the objective of this particular project. So the project scope is develop a cloud-based predictive maintenance system using artificial intelligence and machine learning to collect, analyze onboard vehicle diagnostics, predict turbocharger failure before DTC codes are triggered, and alert maintenance teams for proactive servicing. All right. So this is the project scope. Now, talking about the data sources, these are the source and description. Now, ECU diagnostic data trouble, diagnostic trouble code, freeze frame data, ECU IDs and UDS $22. Now, talking about CAN bus signals, boost pressure, EGR position and RPM, etc. Now talking about the telematics unit, the GPS, driving patterns and idle time. And talking about environmental data, temperature, altitude and humidity, and maintenance history logs, service repair and failure timestamps. So these are the various data sources and these are the descriptions. Now these are the data sources from which we are going to develop a model which is going to finally be implemented as a proactive predictive maintenance. Now, what are the feature engineering comprise of? Engineering comprise of engineers design features such as average boost pressure per 100 kilometers, pressure fluctuation index, percentage time with EGR above threshold, and RPM pressure correlation coefficient, and number of minor DTCs before failures. Now, turbo actuator response delay from IO control tests. And feature engineering was critical to turn CAN UDS data into usable machine learning inputs. So these are the various kinds of inputs that need to be taken into consideration. I mean technical inputs, technically strict for IC engines or technically strict for turbochargers. Now in the machine learning model, all right, we are going to see the various parameters and also the description. Now model type means gradient boosting, the target variable binary turbo failure in next to 500 kilometers, data volume 18 months of data from so I hope all of you getting a magnitude of the getting idea about the magnitude of the project. So in 18 months of data from 850 trucks, and you take care of this training and test split 70 to 30, accuracy 91%, precision 89% and recall 93%. Very important to catch failures early. So these are the various parameters that need to be considered. And talking about the architecture that need to be deployed, the first architecture is edge telematics device. In the real-time onboard diagnostics and CAN data collection, runs lightweight anomaly detection, and cloud backend AWS IoT core plus SageMaker, and receives pre-processed data streams, executes ML interference to assess failure probability, and stores data in S3 and RDS for historical analysis. Talking about the dashboard and alert system, maintenance managers seek risk scores, flags vehicles predicted to fail in next 500 to 1000 kilometers, and generates service tickets and schedules appointments. Okay, so these are the various deployment architecture. Now, what are the various results? All right. First of all, we have one metric in this table. We are going to talk about the metric, the before PDM and after PDM implementation. Okay. Now, before PDM, turbo-related failures for 68 per month. Now, after PDM implementation, it is 11 per month. Towing incidents were 32 per month, and now after the implementation, 4 per month. Average downtime per incident 14 hours, and now 3.5 hours. Because we are able to identify the mistake or the forthcoming error previously, we are going to, or we have the capability to nip the error in the bud itself. And talking about that's the reason downtime can be 3.5 hours. And talking about maintenance cost, truck month and rupee cost is 7,200, and after PDM implementation it is 4,600. All right, and return of investment before the deployment there was absolutely no return of investment. Now almost 3.6 return of investment is there. So because of this project, this much of profit, monitored profit, is being enjoyed by the company Fleetco. Now, talking about the additional enhancements, integrated water diagnostics to remotely verify DTC conditions, used unsupervised learning to detect novel anomalies, and incorporated driver behavior scores to refine risk models, that is harsh acceleration, overspeeding, etc. All right. Now, what are the challenges faced? Now, in the challenge, solution implemented. This inconsistent first challenge is inconsistent sensor calibration. So this whole project cannot be implemented accurately if sensor calibration is not consistent. And to prevent or to face this challenge, what is the solution or applied upper thresholds for vehicle model? And missing historical labels, used heuristic labeling and domain expert review. This is noisy signals from CAN bus and applied rolling average and Kalman filters. Connectivity gaps in rural areas, and implemented edge caching in batch uploads. All right, these are the various challenges faced. Now, talking about the conclusion, the fleet course predictive maintenance project demonstrates successful real-world application of AI/ML in vehicle diagnostics by leveraging CAN plus UDS data plus ML analytics. Now, they prevent unplanned failures, reduce costs, and improved fleet uptime and customer service reliability. So because of this project, these are the benefits that Fleetco is enjoying. Okay, so hope all of you got an idea about this project and how benefits are reaped out of implementing this project.